Hey everyone, welcome to the user group, Pittsburgh.NET user group today. We have an exciting topic. If you'd like to join our group, please follow this meetup.com/PGHDOTNET. We are also on LinkedIn, Twitter, and if you'd like to present in our group, feel free to reach out to me or leave me a message on this. Today we are going to look into from ancient Greeks to modern geeks, machine learning, basic machine learning algorithm. And Simon is not a new person to our group. He has presented already in our group. I'll let him talk through that. Simon, I will pass it back to you.
Woo, and I'm in. If will I just before we begin, will I be able to see any comments in the? There we go. If I go to comments, hopefully I'll be able to see. If I join the chat, I'll be able to see any comments there, won't I?
Yep.
Sorry.
Sure, I'll do that for you.
Yeah, I should have connected that all in before I started. Apologies, everybody. I just would like to give everyone a chance to ask questions if you have any. And then I'll get started. There, and I'm in. There. Right, okay, let's get going. So this is going to be a talk about basic machine learning algorithms. Hence what is meant to be the goddess Athena there. This is AI generated. I didn't have the time, so I think her eye color's wrong and wears a shield with a picture of a gorgon on it, and the helmet's definitely not right. But anyway, fine, it'll do. I'm going to talk about the very basic machine learning algorithms. So I'm going to talk through each one of them because I'm in the process of learning all of this stuff myself, and it's a marvelous way to learn to give talks like this. Plus, it gives me a chance to tie in one of my other favorite obsessions, which is ancient Greece. Because why not? I write these talks. I can do what I like. Let's see if I can. No. There we go. So, aspazume to everybody, because, like I said, I like a good ancient Greek. So you might find a bit of a few references here and there. Am I going to focus that? Let's see if I can fix that. There we go. I think I'll do. Right. So briefly about me, in case anybody is especially interested. I have been in the IT industry for going on 2 decades now. I've worked in all variety of places, mostly UK based, not entirely. I was briefly one of those contractors that your mum used to warn you about. These days I work for a dairy company called Müller. They are particularly well known in the UK for a rather delicious brand of yogurts. I'm not aware that we have a US presence particularly, but if you're ever in the UK, the yogurts are very nice. Someone says the video is choppy. Well, it's fine for me, but of course I am literally live, so hopefully that will resolve itself. I'm also the author of this book here. This is a C# book. Now, this is not going to be a C# talk. I'm going pretty language neutral, but nevertheless, it feels rather a foolish idea not to at least mention that I wrote this here book. So if anybody is interested in interesting and new ways to do C#, do feel free to pick up a copy and let me know what you think. If you scan this URL here, I believe you'll get a month or so free on the O'Reilly platform. So dig in. I can bring that back if anyone wants. So let's talk briefly about what exactly I mean by machine learning, because the terms AI and machine learning tend to be very overused and overloaded these days. So just to explain, machine learning is a subset of AI. That is, all machine learning is AI, but not all AI is machine learning. So there are other things. I am only going to be looking at machine learning. There is a subset of machine learning called deep learning, which you may have heard of. I am not going to cover that. So I'm covering the sort of middle stripe of this weird Venn diagram thing, just the machine learning bit. But before I explain what machine learning is, I want to talk about a big pile of rocks. Because there was an ancient Greek philosopher many millennia ago who came up with a philosophical paradox, and it was the paradox of the big block of rocks. So big pile of rocks. So imagine that I've got a rock and I put it in as the first rock in my pile, and I could ask you, is this a big pile of rocks? To which you will probably reply, no, it is clearly not a big pile of rocks. It is a single rock. Okay, so far so good. I will take another rock I put it. I have now got 2 rocks. Is it a big pile of rocks now? No, it's 2 rocks. Still not a big pile of rocks. So, okay. And then this process can continue for some time and for some time. And eventually, I will have put enough rocks on the pile and you'll say, yes, it is now a big pile of rocks. Great. Okay. So I'll just take one off. Is it not a big pile of rocks anymore? Which is not quite how it works. The point is that something like how many rocks makes a big pile of rocks, it's fuzzy. It has a fuzzy definition. That is, it is hard to quantify in rules that a big pile of rocks equals 7. And if you did that, that would be ridiculous because there are all sorts of other factors. What if the rocks are only this big? A pile of rocks that big of 7 would not be very big. So lots of factors have to be taken into account and they have to be combined in various ways to make a decision, big pile of rocks or not, and it's not simple. The traditional style of computer coding would involve giving simple rules like I said, a definition, it's 7 or whatever. And machine learning enables the computer to make decisions based on fuzzy, hard to quantify decision boundaries, like, is this a big pile of rocks? You can feed it any number of possible inputs and then allow the computer, or the algorithm rather, because we're talking about algorithms rather than computer programs, to make that decision for you and come back with some surprisingly accurate results, depending largely on the source data and various other factors. So you're not going to end up knowing enough about machine learning at the end of this to go away and start a career, because it is an entire career path. It is an extremely detailed, extremely deep field of study, and almost every slide in this talk could end up being a talk all by itself. This is going to be a little whistle-stop tour to take a sort of a gentle snapshot of the sorts of algorithms that you might use. This, by the way, is called the Sorites problem. Sorites is ancient Greek for a heap. I'm learning ancient Greek, so I got to use this stuff somewhere. I'm just a nerd. So my first data set. Oh, hello, Carl. Hello there, my friend. So my first data set. Now, like all good parents, I like to play games with my children. And like all good nerds, I want to make sure that I beat them. So my first question is, can I use machine learning algorithms and statistics to beat my children at super top trumps? Now, I am aware that I'm addressing a non-UK audience, so I'm not sure whether you're going to know the rules to super top trumps Harry Potter edition, which happens to be the edition that my children have. Okay. Here is a Super Top Trumps card, at least Harry Potter edition. There are many, many, many editions of Super Top Trumps. What we have here is a picture from a very popular series of children's novels, rather specifically from the film, and there is a series of statistics down the bottom left. The first year, the length of wand, family tree, fear factor, that is how scary are they, and Super Top Trumps rating, which means, honestly, I don't know, but it means that. What you would do is you would take the deck and divide the deck equally between the players. So each of you have got a little deck of cards which consist of a subset of the whole deck. The first player would draw their card and then choose one of their statistics. And then everyone else will say what their value is, and whoever has the highest value of that statistic wins, and wins all the cards currently in play. And then that player now is the active player and will make the next choice. And you'll go on again and again and again until somebody owns all the cards. It has the potential to last literally forever, particularly when playing with my 8-year-old. So, and incidentally, in this case, first year wins by being low. So the longest ago that you were at Hogwarts beats someone who was at Hogwarts more recently. All others win by being high. Okay, so that is the basic rules of Super Top Trumps Harry Potter edition. And here, because I am that level of sad, is all of the statistics from all of the cards which I went and pulled. Notice there's a lot of unknown values. That literally means that on the card it says unknown, and actually the rules are ambiguous as to what to do when you have an unknown value. In a real machine learning algorithm case, when you're creating a whole a whole pipeline of data processing, you might well try to fill that in with some sort of value, maybe the average of all of the values of that field that exist, or you could use all sorts of other factors to try and make a decision on how to fill that blank in order to allow you to continue. But for the purposes of this demonstration, I'm going to keep it simple, and I'm going to just ignore that for the purposes of these demonstrations. But there are ways of dealing with that in a machine learning scenario. So a couple of basic statistics. So before we get really started, we're going to start with some statistics, because little secret, machine learning really is just statistics. I mean, fundamentally, there is very little that you can do about machine learning that can't be picked up from a statistics textbook from the 1950s or something. The difference is that we're now using a computer to apply our statistics, which means that the computer doesn't get bored, so we can try all sorts of different combinations in seconds, and it never makes errors, and it doesn't mind crunching vast quantities of data, which a human being might struggle with. So there's the difference. So min and max, that's pretty obvious. Mean, median, and mode. So when most people say average, they are actually misusing the term, usually. I mean, it's good enough in colloquial speech, fine. But when most people say average, what they mean is mean. Mean is, the sort of stereotypical average calculation, add them all together and then divide by n. That's mean. If you say average to a statistician, they'll probably look faintly confused at you because you haven't given them enough information. So there are two other kinds of ways of doing this. There's median, which means put everything in a line in order and then pick the one in the middle. Or if there's two in the middle, then you take an average of those two. That is a mean of those two. And then there's mode, which is the most common value to be found in the entire data set. If the data in question is what's called normal form, that means that you have that traditional bell curve shape. If you stack up the values on the bottom and how many of them there are going up the y-axis, you get that sort of bell curve where there is a mode value in the middle, and then everything kind of slowly slopes off from it. Well, if we were in normal form like that, you would expect mean, median, and mode to all agree with each other. That is, to have roughly the same value. Now, what you see here is that actually they don't. They don't agree. They are not all roughly the same, which suggests that there is a large degree of skewing going on. That is, you've got a much longer tail one side than the other, which is indeed what we have. But that would be your first indication that you can't apply things to do with normal forms here on this data set. So a little bit of ancient Greek. Reason being, I have tried my best to render all of these formulae in an algorithmic form, something that might seem vaguely familiar to anyone who knows a modern style programming language or Excel. In fact, I did most of my examples in Excel, but there were one or two where it got too cumbersome to not just use some mathematical symbols. So if you ever see that one that looks a bit like a wonky E, that is sigma, and that means take a sum of all the values in a set. So if you are, like myself, a C# developer, then that would be a link expression .sum. I think it's just sum in Excel as well. Mu there, the one that looks kind of like a U with a tail at the beginning, that is the mean of all values. So add them all together, divide by the number you got. That's what that means. So just so that we have some common terms. So we want to get some more statistics out of our data set to try and tell us a little bit more about what we can see here. So variance is the amount to which we vary from the mean. So what you do is for each item in the number set, so take all the numbers in a particular column, add them all, and we first calculate n1, which is equal to n, whatever n is, that is the current number, minus the mean of the whole number set. Okay? So go through each one in turn, take n, and then deduct the mean. And then get n2, which is the previous value, squared. You'll see a lot of squaring going on. There are a couple of reasons for that. The first is that by squaring a value, you force it to be positive, because a negative multiplied by a negative is a negative, and so on. A square is always positive. Okay, and The second reason is that it kind of skews outlying values to be much higher. So if you've got a whole load of noise around the mean line, or for example, then that doesn't matter as much as an outlying case, which is way over there. That will have a disproportionate effect on the way the data skews, which is what we want. You want variance to skew the data because it's called variance. That's what it's for. Okay, so we have gone through every number in the set, and in each case deducted the mean and then squared it. And then what we do is add together all of those n2s and then divide by the number that we've got. And that is variance. Then if you want standard deviation, you literally just take the square root. So variance has its uses, but in most cases, with fairly standard data, you'll often deal with the standard deviation. So standard deviation represents the amount to which we vary from the mode, in fact, either way. Incidentally, the reason for median and mode like that is that mean, median, mode is that mean tends to be more affected by outlying data items, whereas median tends to be less affected. So in cases where you have a huge amount of variance, median is often a better choice for what you consider to be your average. If this were normal form, then we'd expect about 68% of the data items to fall between mean plus or minus one standard deviation. So in the case of year, that's 1972 minus 23 or plus 23. I'm not going to work out what that is because my mental arithmetic is shocking. But that is still, in most cases, that's quite a lot of variation going on, as you can see. So the standard deviation of, for example, fear factor, the mean is 4. So we might expect to see most of our data items between 2 and 6. And since the min and max are 1 and 10, that's actually one standard deviation either side covers nearly all of our data by the looks of it. Super top trumps rating, the max and the median kind of agree with each other, so it looks like there's more stability in that. In family tree, we've got a min max of 0 to 10, and we're starting around 6 as the mean, and the standard deviation either side will actually take you between 0 and 12, literally all the data. So there's something clearly a bit squiffy with family tree. And if we render this in graphical form, you can see that all of those suppositions are entirely true. We've got a huge amount of skewing. In fact, what you see generally, if I were trying to choose a good card in Super Top Trumps, what I would probably want to do is take the mode, and then because the mode seems to exist at either the beginning or the end of the set, and then it tails off slowly. So with the exception of wand length, which appears to be to have a mode which is right down the bottom. No, Carl is saying that none of these are a normal distribution. Quite right, none of them are. These are no normal distributions here, so we can't do any of that normal distribution arithmetic. But there are some interesting outliers. And what you decide to do with outliers is another decision that you can take. I don't know if anyone can see my mouse. I think it should be visible. So if we have a look at first year over here, we've got this outlier which is way before 1900 in first year at Hogwarts, which is of course Albus Dumbledore. Take him out and actually the mean and medians and stuff start looking more reasonable because he's such an extreme outlier. And over here we've got in family tree, that is how many people are in your family tree known. Then you take these guys here, all these outliers, the Weasley family. This is literally the Weasley family here, and everything else is kind of clumped together over here. Fear factor's nearly normal-ish, but not great. Top trumps rating, it turned out it's pretty much just flat, like that. Fair enough, so it's pretty much just probably assigned one value to each person. So it gives us an idea of what the shape and the feel of our data set is, which is the first stage in trying to decide what on earth to do. So we can also try and calculate how correlated our data sets are, our data items are. So this is to what extent does column A correspond to column B? And here is the algorithm for doing it. Okay, so in this case, X and Y are two different columns. I say dataset, dataset's as good a word as any, but if you were working in Excel, this is a column, X column and Y column. Then go through each of those and calculate X minus the mean of X, Y minus the mean of X, multiply those together, square A, square B, and then finally, your correlation value is AB, that is A multiplied by B, divided by the square root of the sum of A squared multiplied by the sum of B squared. And don't ask me to explain why that is, it just is. It really, yeah. But this is going to give you a value between -1 and 1, where -1 means that they correlate perfectly, but in opposite directions. As one goes up, the other goes down. 0 means they have absolutely no correlation. They are random data in relation to each other. And 1 means they correlate perfectly in the same direction. That is, as one goes up, the other goes up. Not necessarily the same values, mind, but they move up and down in the same way, to the same extent. And this is what our correlations look like for every field in the Super Top Trumps Harry Potter edition compared to every other. I used Python incidentally to generate this. There is a library in Python which will allow you to generate these rather nifty graphs. So the diamond of ones going down the diagonal there, that's the same field compared to itself. So of course it correlates perfectly with a 1. But everything else, think of it as a percentage. Multiply it by 100 in your head and think of it as a percentage. The percentage to which they correlate. So you either want a large negative or a large positive value to consider it significant. Now, none of these really quite count as genuinely statistically significant. There is some correlation. Now, could they be significant? They might or they might not. This is where you probably need to have a chat with J.K. Rowling to find out. But there is a 0.4, that is a minus 40% probability correlation between the first year and wand length, meaning as first year becomes a higher value, wand length goes down and vice versa. So could that be indicative of a change in fashions in the Harry Potter world, that people have preferred shorter wands with time? Could be, could well be. Fear factor correlates negatively 42% with having more family. So the more family you have, the less scary you are. Now, yeah, I can see that. I can see that. So with a large family, they might well be a less scary, more well-balanced person. The obvious opposite of that would be Lord Voldemort, who, of course, famously has no family, certainly by the end of book 4. And incidentally, little trivia point, literally everybody mispronounces his name. The T is silent. It's Voldemort. But literally everyone says it wrong, to the point that you might as well just carry on with the wrong pronunciation now. It's French, means flee from death. That's about. Oh, there is also a 43% correlation between Super Top Trumps rating and wand length. So does that mean that the longer your wand is, the more awesome you are? Maybe. I don't know. Probably not. That might just be a case of random statistical drift. Who can say? But these are still interesting data points. If I were further exploring the statistical world of Harry Potter, those are some of the hypotheses that I might follow. So let's move on to something a little bit more interesting, something where I can draw some better conclusions. So I'm going to look at Pokemon, one of my other hobbies. I am an avid player of Pokemon Go. So I gathered a whole load of statistics, which I found on a site called Kaggle, all about all of the Pokemon. Well, nearly all of them. I think it stops at about Pokemon 800 and something, which is good enough for the purposes of getting some statistics out of this. So I've got attack values. Egg is, I think it's the number of steps required before you get an egg out of this particular Pokemon. There's attacks and defense, weight, all sorts of things. There's loads there. And is it a legendary? Meaning, is it an unusually rare and super powerful Pokemon, like a Mewtwo or something like that? So great. And there's enough data here that we can probably start pulling some interesting correlations. So let's have a look. What we got? Right, there is a interesting few correlations here. Now, actually, about the strongest one is the correlation between Pokemon number and generation, which is at 99%. Now, That's true, but it's also useless because the generation is an arbitrary set of Pokemon, say about 100 and something, which are released every few years, and it just indicates which set were they in, and the number is basically like an identity value in a database. So yes, it's true they correlate, but that is of no interest whatsoever. So what else have we got? 87% correlation. The number of steps required to get an egg with being a legendary. Well, legendaries don't give many eggs, so that is completely reasonable and a strong correlation. So that's terrific. What else have we got? Happiness negatively correlates with being a legendary. Oh, how very sad. What else? We've got some other negative correlations. Defense negatively correlates with capture rate. Interesting. And there's a few other things. 63% correlation. Now, this is possibly the interesting one to start chasing. 63% correlation between height and weight. Now, that makes sense. The bigger something is, generally speaking, the heavier it gets to an extent, as we'll see. But there we go. That's actually a really strong correlation, 63% compared to almost everything else. Everything else that's of any interest. So let's chart it. This is a scatter graph of height versus weight. Now, it is really scattered. And the reason for that is, of course, we are comparing Pokemon of different species. And you can see that they never had the idea that they were trying to make a consistent set of data when it comes to these things when they were designing the game, when the first edition came out way back in, I think it was the 80s or something. And you've got some really random outliers. There's probably stuff like Whale Lord, which is a giant whale thing. It's colossal, but it flies around in the sky because it hardly weighs anything. And then you've got steel Pokemon, which are tiny, but they're made of steel, so they're incredibly heavy. So you're going to have all sorts. But broadly, there is a sort of tendency to follow a nice line-ish. So we can actually start to prepare something with our very first algorithm, which is to try and draw kind of a best fit line. You know, the line that approximates to the best extent we can the equation that transforms one of these data sets values into the other. That is, given weight, what's its height, and vice versa. It's called linear regression. So here is the algorithm. Oh, it was 1996. Thank you, Carl. I didn't own one of the consoles back in those days, so I never got to play it. So linear regression. This is to make a best fit equation for converting between the data sets. So X is our source property, what we're coming from. Y is our destination property, the one we're going to. So we're mapping two continuous data items, mapping the what do you call the units of one into the other. So go through each one, each X and Y, and we're going to generate XY, which is equal to X multiplied by Y, X squared, which is X by itself, and Y multiplied by itself. Okay, so we've got those items out of it. So to make a linear equation, we need a gradient and an intercept. So the intercept is the point at which the x-axis the line crosses the x-axis, and the gradient is the angle. So once we've got those two, we have ourselves a line. And the intercept is equal to the count, that is the number we've got, multiplied by the sum of x multiplied of xy, minus the sum of x multiplied by the sum of y. Take all of that, divide it by the count multiplied by the sum of x squared minus the sum of x squared. Subtly different. Sum of x squared or sum of x squared. I can't even say them without sounding the same, but there you go. All of that, plug that into Excel or whatever, and then you get your intercept. Take that value, and then take the sum of y, deduct the intercept multiplied by the sum of x, and then divide all that by n. Great. Do all of that, and you've got yourself an equation line. So y is equal to intercept plus gradient multiplied by x. So if you need to know what the y value is for a data set, there you go. Here is the equation then, using that exact formula for the weight of a Pokemon given its height. So if I can take the height of any Pokemon, then to work out its weight approximately, I would multiply it by 63.5 and then add minus 12.5. and there we would have approximation of its weight, which is great. Now, is there a way to find out how accurate we are? There is. This, by the way, is the equation line plotted against the data set as a scatter. You can kind of see it roughly falls in the middle, so it's as good an approximation as you can expect to get. So there is a way of calculating how accurate we are, and that's error, or it's called R squared, strictly speaking. R squared. This is the fitness for purpose of your model, and it represents the percentage to which your model explains the variance within the real data set. So calculate the total sum of squares, TSS, which is equal to, for each y, go y minus the mean of y, square it, and then add all of those together. And then the residual sum of squares is equal to, take y, deduct the calculated y, that is y run through the algorithm that I just calculated, square it, and add those all together. And then do 1 minus RSS over TSS. And that will give you 1 squared, which is going to be valued between 0 and 1. 0 meaning they are unfit for purpose, and 1 meaning they're perfect. So the closer to 1 that we get, the higher the value, the better. It's a percentage again. There you go. So based on that, I ran this equation for every single item in the entire Pokemon dataset, and then compared that using the algorithm with the actual value. And what we got back was a fitness for purpose of 39.7%. So my algorithm explains 39.7% of the variance. It's okay. It's not great. But as I said, there is a lot of random scatter, but it gives you an idea of how this process works. So let's have a look at an example of some data items where there is a perfect correlation, where it works exactly right. So these are a few items of data that I scavenged off the internet. The first column there is a year, as in a calendar year, and then after that you've got the 2 different data items. Now I'll explain what they are in a minute, but they correlate really well, and I'll show you. There we go. This is me running things through Excel to get my A, my B, my AB, and so on, all my values that I need in order to calculate my equations. And they have a correlation of 96.39%. That's incredibly high. They correlate really well. That's not to say they're the same again. That's just to say that they match each other's behavior as time goes on, whatever these data items are. Great. And this is them on a scatter graph, and you can see that is really linear. That's one data set as the x-axis and one as the y, and then on a scatter chart, you can see that's really linear. So let's have a look at calculating some error and some gradient intercept and all the rest of it. So gradient is 603, so that means intercept is minus 7653. So the equation is take x, whatever that is, multiply by 603, and then deduct 6,554. And then you'll have the y. And that's what that looks like plotted against each other. The orange is actually my prediction, and the blue is the real data over time. So it bounces around in some strange ways, but still, broadly speaking, it is mirroring the real world. The R squared, that is the fitness for purpose. How good is it as a percentage? 96.4%. This is terrific. This is an excellent fit. So actually, what these data items are the total revenue of the company Google correlated with the sales of cheese in America. Now, it's unlikely that these actually correlate in any meaningful way. Well, they do correlate literally. You can see the data items correlate, but correlation does not equal causation. The relationship between these two is esoteric at best. I mean, it could be that there are mysterious underlying factors that connect these two. Maybe it's something to do with the state of the American economy, or I don't know, but very likely it's just random chance that they happen to roughly correlate with each other. Or maybe it's inflation, I don't know. But you've got to be careful, is my point. Just because 2 data items seem to match well, you still need an understanding of the data that underpins it to be able to decide whether there's a true correlation or if you've just noticed a pattern in the noise. Because statistics are noisy. Right. So what about multiple linear regression? That's the next one. So this is the same idea as your linear regression, except now we're not just going to feed our algorithm one column, we're going to feed it a whole load of columns. Carl says, I remember a great story where someone plotted all the ley lines between ancient stone monuments in the UK. Yes, I know about that one. And someone else did the same for Woolworth stores. Yes. Yeah, pretty much if you take any sort of a data item like that, you're going to be able to find lines. It's just the way it is. Yeah, there was this story going around for some time that there were these mysterious ley lines which connected all ancient sites in the UK, and they don't. It's just the way that things all line up. But yeah, you've got to be careful. And famously, there is the Church of the Flying Spaghetti Monster, one of the great religions of the world, of course, who came up with an amazing correlation that the average global temperature correlates negatively with the number of pirates in the world. So if you were to apply correlation and causation from those, you would have to conclude that we all need to quit our day jobs, become pirates in order to prevent global warming from occurring. And of course, that's nonsense. So anyway, be careful with correlations sometimes. So yes, now we're going to have a look at how do you feed in several columns, and then try and use those together to make a prediction. And will it give you a more accurate prediction? I'm going to have to use some matrices in order to do this. Now, unlike these people here, real matrix has got absolutely nothing to do with strutting around in sunglasses and storm jackets. It's just a table of data. I think the guys who made the Matrix just thought it sounded cool. A bit like the folks that made the film Source Code. I don't know if anybody's seen the film Source Code. I quite enjoyed the film, but what on earth has that got to do with source code? Nothing. The computer, for some reason, is called source code. That must get confusing for the developers working on it. Got the source code for source code? Sure, I've got the source code for source code. Anyway, so a matrix is just a grid of data. It's just a two-dimensional array, if you like, or a block of data in an Excel spreadsheet. And there are processes you can do with matrices, which combine them to make a new matrix. Effectively, this is a really shorthand way of doing a whole load of tedious sums. So, for example, if you want to calculate this orange square, so when you do the multiplication between these matrices, you get a new matrix which is equal to the number of rows in this one, the first one. The order matters. The rows in the first one to columns of the second one. Okay, so it's 2 by 2 is the new one. And to calculate this one in the 0, 0 position here, that is equal to taking each of the, yes, XA, XB, yeah, XA multiplied by AX, that's this one, 1 by 1, add 2 by 1, multiplied by 1, add 4 multiplied by 2, add 5 multiplied by 3, add 7 multiplied by 7. And then add all them together and you got this one. So as it happens, it's 75. That would take ages to write out. So doing it in matrices is a shorthand way of doing all of those sums. And I'll get on to how we're going to use them in a minute now. I didn't sit down and do all of these sums. In fact, Excel has got a function that does all of this for you. And that's my complete matrix. So I do complete my multiplication. There are a few, these are the three matrix operations that we're going to use. Now I'm using the names here, which are given in Excel. So you've got matrix multiplication, it's mmult in Excel. Transpose, which is take the rows and turn them to columns, columns to rows. So sort of flip it around. And then inverse. Now, I did consider explaining the rules of inversing a matrix, and they're really horrible. They're really complicated. If you've got anything much more than a 2 by 2 matrix, then inversing it becomes just nasty. It's the matrix equivalent of turning X into 1 over X. That's really all you need to know. I am not going to go into the math of matrix inversing. So how do we go into a multiple regression? So I've picked out weight again from my Pokemon set, and I've picked out each of the items that I think have the strongest correlation to weight. So I've picked the height in meters, which I already had, the number of steps required to hatch an egg, and the defense value. Okay, so this is the algorithm that will get you an equation out of this that will get you a new weight based on 3 parameters. And you can expand this to as many parameters as you like. This is a completely generic process. So first, you make a matrix of the actual y values, that is the values you want to achieve. And that is a 1 across and n down matrix. Then you make another matrix which goes down by n again, but each column is, the first column is a column of 1s. It's just literally a column of 1s. And then each of the other columns are your data sets that correspond. Okay, so far, so good. Transpose it, that is, flip it around. Multiply it, that is, take the transpose, multiply it by the original, and you get back a new matrix. Inverse it. Then take that inversed one and multiply it by your original inverse, the first inverse matrix that you made. Take that and multiply that by the original y column. And then what you get back is a 4-element matrix. It's almost magic. I don't really understand all the fundamental maths of how this works, but what you get is a 4-item matrix. The first item is the intercept, and then the others are the multiplication factors for each of your parameters. So that means my new updated equation for calculating weight is minus 70.5 plus height multiplied by 48.5 plus egg steps multiplied by 0.003 plus hit points multiplied by 0.7. Stick all of that together, and we get an R squared of 47.26%, which is a significantly better result. It's still not amazing, but it is a much better. Here they are compared. So the original single linear regression was 39.7. We're now on 47.2. And it could be that there are ways of enhancing that a little further, but I suspect to a degree you're always going to get a slightly rough result just because of the nature of how scattered the data items are. Now, there are other algorithms which should probably be more appropriate, and we'll cover some of those in a bit now. So, logistical regression. This is similar to linear regression, but there's an important difference. Okay, linear regression and multiple linear regression are based on the assumption that each of your data sets is linear. That is, they have a range of values, and you can be literally anywhere inside the range, anywhere. It's a continuous value, and you can pick whatever decimal value you want. Okay, logistical regression is based on the idea that what you were trying to get out at the end is a 0 or a 1. It's a probability. So that's what we're trying to get. We are trying to get we're not trying to transform one range of values into another. We're trying to take in a set of values and then assign a probability that a given condition is true. So I am going for, is this Pokemon a legendary? A legendary in the Pokemon world is just a large, rare, and unusually powerful Pokemon. So this Dialga on the left is an example of a legendary. The little annoying Pikachu on the right is not. So looking at the correlations along the is legendary line, it's the one at the bottom, by the way. There we go. Let's zoom in on it. What correlates to being a legendary, other than is it a legendary? Because we're not allowed to use that one. That would be cheating. The number of egg steps is pretty good. The amount of happiness, because apparently they're less happy, the poor things. How easy it is to capture them, which makes sense. There's a minus 33 correlation to being easy to capture. Their attack value, which again makes sense. They are more powerful generally, and their weight. All of these are pretty good correlations, and we're going to use those to try and make a guess on if a given Pokemon is legendary or not, just based on those stats and nothing else. So first off, you run this through the multiple linear regression algorithm to get yourself a multiple linear regression equation back. But that's just the first step. Then you take that and divide by, so you take the exponential value of it. It's the exponent is x multiply x raised to the power of 2.71, and then a great big long irrational number. Excel has got a value in there. It's exp. In C#, it's math.exp or something like that, or math.e. So you don't need to worry about that exactly, but it's a maths thing. Okay, so basically raise the probability is legendary value up to the power of 2.7, and then divide that by 1 minus that same thing, and then you get back a probability, the probability of whether it's true or not. So here is an example of the probabilities they're on the third column there, and the first column is it the actual truth. And what I notice is that whenever it's true, like these three here, it's about 0.64%, 0.63, 0.63, and then we drop down to about 5.3, 5.4, 5.4. Again, these are probabilities. And then here we've got ones that we're up to 0.7, 0.7. So it looks like it's never going much below 0.5, which is a 50-50 chance. But whenever it is actually legendary, it's at least 0.6. So I'm going to say, based on this, that my rule is that if the calculated probability is 0.6 or better, then I'll say it is a legendary and anything else is false. So let's see how I did. There we go. This is a pie chart. I've got 4 sections on this. True positive. That is, I thought it was true and it was. False negative. That is, I thought it wasn't, but it was. True negative. That is, I thought it wasn't. And then false positive. I thought it was, but it wasn't. So the actual number of these that I got correct is 729 plus 63, which is 780, 790 something. And then the number I got right is 7 plus 2, 9. So it's 98.88% correct. That's not bad. I can live with that. So moving on to another algorithm, we're going to abandon the world of Pokemon, and we're going to go to one of my other favorite geeky things, which is Doctor Who, because I am a massive, massive fan of Doctor Who. Right. I am going for statistics about the number of stories that each Doctor had, and don't anyone start arguing with me about how many stories each Doctor had, because I know how incredibly complicated that question is. These are the numbers I've gone for. You can feel free to argue them, but these will do. And then I've gone with how many of these stories had the Daleks, the most popular bad guy in Doctor Who, as the primary bad guy. And so in order to count on this, they have to be the main baddie and not just wandering around in the background somewhere. So I'm interested to see what we can do with these numbers. So this is a naive Bayes classifier. It's a way of reordering probabilities, kind of like doing a group by. But regrouping probabilities from groups by one thing into another. Okay, I'll show you what I mean. So first off, we can calculate the probability of, is there a Dalek in it given the Doctor? So that means, for example, first Doctor, William Hartnell, he had 29 stories, of which 5 had the Daleks in them. He had them quite a bit, but then it was the beginning of the series, so of course they were bringing them back all the time because they were incredibly popular. Which means that the probability of is there Daleks, given that we're looking at a first Doctor story, is 17.2%. That is 5 over 29. Whereas over in, I don't know, Jodie Whittaker over there, she also encountered 5 times, but she only had 24 stories, kind of. So we have actually a higher probability because proportionally that was more. So 5 over 24 is 0.20. That's 20.8% probability. Right. Fine. And I'll start showing you what naive Bayes can do with these. Naive Bayes can switch it around so that rather than being a probability of A given B, you could switch it around to a probability of B given A. So what does that mean? So the probability of A, so we can switch it from, here's a bag of random first Doctor stories and a bag of random second Doctor stories and a bag of random third Doctor stories. And then we can take all of those, merge them and resplit them. And what we end up with is a bag of all Dalek stories, and we can pull out of that what's the chances that it's the first Doctor or the second. So it's turning the probability set on its head. And I'll show you how you use it shortly. So probability of A given B is the probability of B given A multiplied by the probability of A over the probability of B. Great. That's the calculation. So we, in this column here, we have the probability of it's the Daleks given it's this Doctor. And down here, with a couple of steps, we've switched it to it's this Doctor given that you've got Daleks. So if I picked a random Dalek story now, I know the probability of each Doctor, so I can even work out the most likely Doctor actually to have encountered them, which is, okay, it's William Hartnell, which I probably could have predicted at the beginning. But Jodie Whittaker now balances them out at 17% chance. Poor old Shooty Gatware, of course, hasn't encountered them all because he's literally only had one story to date. And yeah, I know David Tennant's in there twice. Doctor Who's like that these days. So here's a slightly more interesting use of this same process. I'm going to use it as a classifier. So a classifier is deciding, is this piece of information a member of class A or class B? So in my case, what I'm going to do is I am going to pull a random sentence out of one of my favorite books, conveniently public domain so that I don't have to get in trouble for copyright breach. Journey to the Center of the Earth by Jules Verne, or The War of the Worlds by H.G. Wells. I am using an English translation of Journey to the Center of the Earth because otherwise it would be too easy. There. So what I want to do is pull a random sentence and then see which book does it belong to. So this is the process that I followed. First, get all the lines out of the book, which I got from Project Gutenberg, which is a giant online repository of all public domain books. It's great. Remove the stop word. So a stop word, you can see a column of them on the right hand of the screen there. This is all words that are so common, so everyday, that they really tell you nothing. We're trying to strip any given sentence down to just stuff that is going to be statistically interesting to help us choose. It might be the word Martian, for example. Were it the word Martian, I could probably make a pretty safe guess on which book that came from. Then remove all the punctuation because it can get, otherwise it will treat yes dot or yes full stop as the same as not the same word as yes. So remove one word lines because there's nothing really I can tell from a one word line. Unless it's, say, Martian. Then remove numerical words, that is actually numbers, because they don't tell us anything either. So we've shredded all of the noise that we can. We kind of pressed it so that we've just got more interesting statistical information. And this is what we end up with. The famous opening of War of the Worlds has been boiled down to one would believe last year's 19th century. And these are lines of each of our books. At a glance, I could probably tell roughly which ones these are from, but then I know the openings of both these books that well. So, and what I'm going to do is calculate my algorithm, and then I'm going to run it against all the lines and see how accurate I actually get. So, this is how you do it. First, you take a word out of the line, the word one. So we calculate the probability of this word given its War of the Worlds, which is 0.0062. The probability that it's Journey to the Center of the Earth, which is 0.00495, and the probability it's a word at all. I am, for the sake of being able to do these equations, assuming there are only 2 books in the entire world, which I know is a false assumption, but it means I can do the maths. So which is the probability it's the word at all added together. Okay. So the probability that is Journey to the Center of the Earth, given it's this word, is equal to the probability of the word given journey multiplied by the probability of being journey at all, which at the moment is 0.5, because I don't know. I'm going to assume it's 0.5. I'm going to assume there's a 50-50 chance, divided by the probability of this word. Run all of that, and we get probability that it is Journey to the Center of the Earth based on the word one is 22%. And the probability that it's War of the Worlds using the same process is actually 27%, 28% really. Weirdly higher, although with simply the word one. Clearly the word one tends to occur a lot more often in War of the Worlds compared to German. Fair enough, but I wouldn't really regard that as a very rock solid diagnosis at this point. That's not enough information. So we've got to now switch to the word wood. We can now do the same thing, but we're going to update our thing. We now have a better idea of the probabilities involved, so we can update our assumptions. Rather than 0.5%, we can use the generated values from the probabilities in the last to run into this version, and so on. So what we end up with is a series of values which are hopefully going to gradually correlate on a correct answer as we feed more and more words into the pile. And this is what it looks like. As you add each word in turn, the numbers get smaller, but broadly speaking, there's a bit of weirdness at the beginning when we don't know very much information. But after about word 3, War of the Worlds stays on the top, and that's it. It's just always on the top. It always has a higher probability than Journey to the Center of the Earth, so which is in fact the correct answer. So based on that sentence, we have now correctly diagnosed that this is War of the Worlds because the probability is higher. Now this is how spam filters work. It's not necessarily going to use words. It might use all sorts of properties, but it's still the same principle. This is how spam filters work. Something that is meant to decide whether something belongs to a set or not based on a series of observations. That's what a naive Bayes classifier is for. So let's have a look at some other ones. K nearest neighbor. So this is a way of trying to work out whether a new data item fits into one of any number of different categories based on its nearness. So naive Bayes can only work out a probability of, are you in group A, yes, no, and then are you a member of group B, yes, no, and so on. And then your answer is whichever one's the highest one. K nearest neighbor allows you to have as many different categories as you like. So first off, when you're trying, you treat all of your data items, all of your data points in your new data item, all of your columns as distances. And if they're not currently distances, then you're going to find some way to transform them into distances. There's all sorts of ways of doing that. For example, if it was male, female, other, then you might use the numbers 1, 2, 3. Those do not imply superiority of one value over another. That is simply giving an arbitrary numerical value to those data items. And that would mean you can then calculate a distance. Okay, and then you calculate the Euclidean distance. That is literally the straightforward distance from here to here. That's the Euclidean distance. Basically, do some Pythagoras. And then order them by the distance ascending. That means the nearest item will be at the top. And then pick the top K. Now, K is however many you want. This is where you tune your algorithm. Pick how many nearest neighbors you want to pick. Take those nearest neighbors out. Maybe it's 5 nearest neighbors. Maybe it's 10. You're going to try a few values. And then look for the most common category amongst them, the mode. Take the mode of the categories. And then that's your answer. That's the category that your new data set belongs to. This works very well as when you have a relatively small number of data points, because you've got to calculate this distance for every data item in your entire back catalogue of data items. But it works very well as well when you've got a lot of noise around the fringes, because the nearest neighbor will tend to make a good judgment, even if there's some noise in there, because as long as it'll take the majority rule every time. So I am going to use the example of color. So labels to colors are really arbitrary. It's actually a continuous value amongst 3 different values, RGB, red, green, blue, and we have arbitrarily assigned names to the different colors, and not every language agrees on what those are. Welsh, for example, has no separate word for blue and green. There are many languages that have no separate word for blue and black. So to them, they're the same color. Italian has an awful lot of words for blue. But fine. I have gotten myself a data set of named colors, which you can see on the left there with their RGB values. And then using that, I use random.org to generate a completely random color. And then I'm going to use K nearest neighbor to decide which color is it. Well, it looks like red to me. if I had to guess. But let's see if it really is. So the distance, it's just Pythagoras, you know, and it's the Pythagoras, and it's the difference in distance. So take R2 minus R1, red 2 minus red 1, square it, green 2 minus green 1, square it, blue 2 minus blue 1, square it, and then take the square root of the sum of all of those, and you've got yourself the Euclidean distance. So the first item out of the first color out of my bag of actually categorized colors is gray. That's 84, 84, 84, and the Euclidean distance is 143.7. And if I run this with every single color and then sort so that I've got all the nearest ones nearest to me, then I appear to actually have found myself a shade of brown. It's sort of brick brown, and brick brown is, of course, a sort of reddish brown, like terracotta roofs, but apparently it's brown. So fair enough, there you go. Nearest neighbor has spoken. So this is my last algorithm in a set. Now, decision tree mathematics is really horrible. I mean, like really flipping horrible. It is so horrible that I'm not really going to give you a full worked example of this, because the mathematics for deciding the decisions and optimizing the tree are so complicated that I could easily do at least 1 or 2 lectures entirely on this subject. Okay, so what instead I'm going to do is kind of give you an idea of the sorts of things the decision tree is doing. So once you understand the idea, then just go and use the tool, because Python and C# and probably all the rest of the programming languages in the world have all generally got a package that you can use to create a decision tree automatically, and it will make an optimum decision tree for you based on the data you give it. But let's see what the decision tree is doing. So I'm going to play a game again. This game is called Guess Who. Now, I'm not sure if you've got Guess Who in America or not, but this is the set that I grew up with when I was a kid. So the game is that you and one other player are going to face each other, and you've got this tray with a set of cards in it that are all face up like this, so that only you can see all the faces. And secretly, each of you has one of these people on a card, and that is your person. You can ask each other yes or no questions only, and based on your opponent's response to your question about their person, you can then flip down a load of people on your turn and attempt to deduce which person is on the card held by your opponent. So how is the optimum way to try and play Guess Who? Well, really, what you want to do is eliminate about half of the people on the board each time, because if you choose less than half, if you chose, say, a question that had a very low proportion of things on this board, then you've got a small chance that you're about to have a really good turn, but a much bigger chance that you're just going to knock down a couple. And then if your opponent asks a 50-50 question, they're going to be well ahead of you in the game. So really, we want to get as close to 50-50 as we can. So how well can we do? Well, we've got hair color. There's about 5, maybe 4 with the same hair color. So that's not ideal, because how many people do we have here? 1, 2, 3, 4, 5, 6, 7, 8. 3 times 8. What is that? 16, 24. So yeah, that's not great. How about gender? Gender 19-5. Now, I don't think this is because of a bit of old-fashioned 90s sexism. I think it's more that otherwise the game would be really unbalanced, because if they went for a 50-50 split, then everybody is literally going to ask that as their first question every single time. How about these? Facial hair, yes, 7, not good enough. Or blue eye color, no. Big nose, no, 6. Rosy cheeks, just 5. Glasses, 5. Hat, 4. That's even worse. So none of these are particularly good for trying to eliminate half of the items from the board on the first turn. So the answer is to combine them into some sort of way of asking the question, so that I can get somewhere close to 50-50. Now, in a real decision tree building process, If this were logistical properties like these, where it's true or false, then this is how I do it and combine them. Otherwise, if it was a continuous property like height or weight, I would probably pick a point on that continuum where it's going to eliminate 50. But in my case, though, I have to use an or property. So my first question is, do you have hat or glasses or jewelry or earrings or bow? Now my opponent's going to hate me, but nevertheless, I'm either going to eliminate 11 or 13 people from that first turn, which will be a very good turn for me. Are you female or you've got facial hair? 13 or 11 eliminated, which is pretty good. I tried to find something that was literally 12-12. I couldn't find anything. If anyone works one out, let me know. My third one was hat or glasses or blue eyes, which is really random, but fine, 13 or 11 again. So that's great. So I'm going to play the game. Let's see who my person is. Question 1, female or facial hair? Oh, those numbers are wrong. Yes, they are either female or have facial hair. So 11. 11 that could be, 13 that aren't. Bam, there's a whole load of people left. Only ones we've got left are men with facial hair or women. Great. So what we have to do now, and this is what the decision tree would do again, try now, given this situation, find another way to split the new data set 50-50, ignoring all of the ones that have been eliminated, and now come up with a new question based on what we now have on the board. I came up with beard or blue eyes, 6 or 7. So I don't really mind which your answer is. I am still pretty much going to eliminate half the people on the board. No. As it happens, my person has neither beard nor blue eyes. We're now down to 1, 2, 3, 4, 5, 6 people, 7 people left on the board. So 2 turns in and we've nearly won. This is the power of this sort of idea. So of these people that are left, how can we try and eliminate 50% of these people? Do you have black hair? Either yes 3 or no 4. No. So we can eliminate a few more people. We are now down to 1, 2, 3, 4 people. So yay, it's not going to be too hard to come up with a 50-50. Again, only looking at the people remaining on the board. And I went with hat. That'll literally take 2 people out of here. Yes, my person has a hat. Which now means that I can simply ask, are you Maria or are you Claire? As it happens, I'm Maria because I always thought she looked so cool when I was playing this game. She looked so cool. But there we go. Now, a decision tree won't just calculate these on the fly each time. What a decision tree would do was use combine logistical properties and find decision points to break continuous properties, and then it will calculate it at the beginning for every eventuality in the training data set to create a whole tree of questions. So if we hadn't answered this one on this path and we went down this path, then there'd be a whole tree of questions on this path and so on. You end up with this complicated branching tree of yes no questions at each point. And then what you would do is put the algorithm together with the training data so that it works out all its questions and its optimal branching strategy, and then push a new data item through it, which will then sort of flick around the tree until you get a decision at the end. That's how a decision tree works. And it's probably one of the more powerful algorithms that can be used in machine learning. But unfortunately, it is just ridiculously complicated. So doing a worked example, like I said, isn't really quite practical. That's all of the algorithms. So if you want to see anything further, these are books which I've personally either used and found very beneficial or have been recommended. So I have a copy of this one, Statistics by Witte and Witte, or Witte and Witte, I'm not quite sure. This is really good. This is a big book on statistics and how to learn statistics. It's laid out in a very nice, easy to follow, logical manner. And really, if you're going to learn machine learning, you've got to start with statistics. At least I think so. I've been recommended this one. I've had a read of it. It's really good. It is in Python, if that bothers you, but it's also available at the URL at the bottom of the screen there for free, which is a very good price. This one I like a great deal as well. I own this one, the 100-page machine learning book. Again, also available for free, although I do, as happens, there we go, own a copy. Oh, actually, come to think of it, and there is my copy of the statistics one, see? But I like to have a hard copy to read, and this book is really good and goes an awful lot deeper into the topic than I ever could in the course of this roughly 1 hour lecture. So, are there any questions? Because this is pretty much it. Shall I? I don't know if I need to give everyone a second to recover from their stunned silence after that load of mathematics. But I'll give everyone a few moments. But otherwise, I'll lurk around. Yeah, there we go. No, I'm not seeing any questions popping in. Just but I can just have the screen back for a minute. I've got a few
sure.
more. Yeah, thank you. Got a few more slides to show then if there's no questions at this point. But, there we go. So if anyone is interested, this is a link here to my GitHub repository. Thank you, Carl. He says that's a great overview. Yes, and you have a lot to learn. Me too. I mean, like, this is a ridiculously deep topic. People literally spend their careers doing machine learning because it's a deep enough thing that it can become your entire career. But I think there's no harm in at least knowing some basics. I'm enjoying slowly getting myself deeper into it. But this repository has got source code for a lot of the samples that I generated during the course of this. So feel free to dig into that if you're interested. This is my blog where I've written out longer form articles of a lot of the algorithms I've covered here. So again, this is a more C# oriented version. I used Excel, to be honest, to generate an awful lot of the data that you saw in this, but this is a very C# oriented version of a lot of these algorithms. So feel free to dip into there if you want a more .NET version of this concept. Once again, is my book, which, you know, I spent a lot of time on it. Please read it. It's very silly. There's a lot of terrible dad jokes in it. And this will answer any questions you have remaining, if you have any at this point. And all that remains for me to do is say thank you very much.
Thank you, Simon. It was insightful. Thank you very much. Thanks, everyone, for joining us today. And we'll see you next month with another exciting topic. Thank you all.
Thanks, everybody.